Hi, my name is Tianjian. I'm very happy to present our work, Upsample or Upweight, Balanced Training on Heavily Imbalanced Datasets, which is published at NAACL 2025. I'm super thankful to my wonderful colleagues, Haoran and Weiting, and my wonderful advisors, Kenton and Daniel. Without further ado, let's get started. Let's first take a look at our language model pre-training data. In our pre-training corpus, there exists very common knowledge, such as where to get calcium. But there also exists very rare knowledge, such as a small species of sea snail. This is called Trivia Mediterranea. If we look into the entire C4 dataset, and we found that while calcium appears over 4 million times, Trivia Mediterranea only appears 4 times. This reveals that knowledge in pre-training data exhibits a long-tail phenomenon, where common terms or knowledge, or even domains such as calcium, can appear millions of times more than rare knowledge such as this little sea snail. Our question is simple. How do we train a model on the skewed dataset so that our model does not overlook the long tail? We mainly introduce 2 solutions. In the first solution, which is called temperature sampling, it oversamples the infrequent domains. Here is an illustration of what temperature sampling accomplishes. It effectively smooths the distribution to a more uniform one. The higher the temperature, the more uniform the distribution is. Here we plot the transition of temperature sampling from temperature equals 1 to temperature equals 3, effectively making the distribution smoother. Here is the mathematical notation of temperature sampling. It simply powers up the domain sizes by 1 over the sampling temperature to form domain weights. As we increase the sampling temperature, we are effectively making the distribution more smooth. Here is the sampling temperature tau. Another solution is scalarization. This is to assign a weight to every domain, and we can assign a much higher weight to the loss of infrequent domains to overcome the long-tailed problems. Here is the weight wk that is assigned to each domain d. We compare this with temperature sampling. We show that the difference is that scalarization applies a multiplier to the loss, where temperature sampling applies a multiplier to the sampling probabilities. The 2 solutions, scalarization and temperature sampling, are 2 of the most commonly used methods to overcome long-tailedness. We look into the literature, which often assumes that the 2 are in fact equivalent and we can use them interchangeably. We want to highlight certain quotes in previous work saying that we implement scalarization with proportional sampling. Although there are also works that acknowledge the differences empirically, they fail to provide a detailed explanation on why they differ. In this case, the author acknowledges the difference but fails to provide an explanation, only saying that we hypothesize that the mismatch between the proxy and main model, which is loss reweighting versus resampling, explains the performance. In this another example, in this author rebuttal, the author mentions that the advantage of temperature sampling is just it is simple and intuitive. Again, it fails to provide a theoretical comparison. The lack of understanding between both methods prompts our investigations on the differences. First, it is well established that under full gradient descent, the 2 are equivalent, as you can simply set the weights to be the ratio between the sampling probabilities with and without the temperature, making the 2 equivalent. However, under stochastic gradient descent, the 2 are not. Specifically, we prove the following theorems. Temperature sampling induces a large variance between gradients compared to scalarization in its SGD. We empirically verify our hypothesis and show that sampling on the left violin plot does have a lower variance than scalarization, which is on the right violin plot. Here is the mathematical notation. Then we further prove that as we increase the temperature, the variance also gets higher. So far, we have shown that temperature sampling induces larger variance, and as we increase the temperature, the variance also gets higher. But what does this theory tell us about model training? We connect our findings to the literature on variance reduction techniques, which accelerates the convergence of SGD, and thus we make the following hypothesis. Due to temperature sampling induces less variance, it should converge faster than scalarization. Let's find out. Specifically, we train a machine translation model on English to both Czech and Romanian, where Czech is the high resource direction and Romanian is the low resource one. We observe that the dashed line, which is temperature sampling, always outperforms the solid line, confirming our theory. Moving further, we found that increasing the temperature from 2 to 5 does accelerate the convergence even more, confirming our theory, saying that as we increase the temperature, the variance also gets larger. However, there's a drawback of using too large of a temperature. Due to heavy oversampling of the low-resource languages, in this case Romanian, it makes the model easily overfit this domain at higher temperatures. Thus, we propose cooldown. Initially, we want to use a larger temperature, then we decrease the temperature to a small one to prevent the overfitting. What motivates our method is that if we just compare using a static temperature of temperature equals 1, which is the green line, and using a larger temperature of temperature equals 5, which is the blue line, we found that the green line converges slower, whereas the blue line converges faster but is easy to overfit. Our proposed method uses a large temperature at the beginning to enjoy the fast convergence, but uses a lower temperature at the end to prevent the overfitting. Our method achieves the best of both worlds, accelerating the convergence, while also not overfitting the low resource domain. Here we use different languages as a case study for data imbalance. We use the natural division of domains, different languages in the world, which has a super heavy domain mismatch. Here is an illustration of how much data is in the MC4 corpus, where the size of the circle is proportional to dataset size. English is much larger than Chinese, Italian, and Swahili, which is the low resource one, is nearly invisible in this figure. We then validate our findings on more realistic tasks under this setting. In this case, we pre-train a 280 million language model decoder only on 4 languages selected from this corpus. Recall that English is significantly more than other languages. We found that our method outperformed other methods using a static temperature of temperature equals 1 and temperature equals 100. We also compare our work with other existing work that dynamically adjusts the sampling temperature with 2 different trends. The first one is order matters, which upsamples low-resource languages at the end of training, which is the exact opposite of cooldown. And Unimax that upsamples low-resource languages at the beginning of training, which is the same trend as cooldown, but removes them entirely. Our work differs instead of completely removing them, we only remove the upsampling part and just sample proportionally. Again, we found that our method outperformed the 2 baselines that we tried. So to summarize, our work investigates the 2 common approaches for dealing with imbalanced data. The first one is temperature sampling, which resamples different domains. The second one is scalarization, which reweights each domain by their losses. Despite the common perception, the 2 are not in fact equivalent, as temperature sampling leads to a lower variance in gradient estimates, and as we increase the sampling temperature, the variance also increases. Connecting with the literature on lowering variance to accelerate convergence in SGD, temperature sampling enjoys faster convergence, but is more prone to overfitting. We thus propose cooldown to initially use a large temperature and then decrease the temperature to enjoy the best of both worlds. We have the fast convergence of using a large temperature at the beginning, but we prevent the overfitting by using a smaller temperature at the end. This is our suggested recipe for pre-training language models on heavily imbalanced data. For more theoretical and empirical results, please check out our paper. Thank you very much.